Okay, so this is our last year that we're reviewing is atomic physics. The one we just did, so it should be the one that's most familiar to us anyway. So I'm going to go a little bit quicker through here than I might otherwise go. Just in terms of formulas or concepts, probably the biggest sort of overarching theme in here that you have to have an understanding of is the evolution of the model of the atom. And you have to know why each model was rejected in favor of the next one and who was involved. So that's why I've given you this second sheet here, and I printed it out separately simply because I wanted to have it in color, because I thought it was a little nicer to have it in color. That basically lists the models of the atom that we talked about and shows sort of a pictorial representation of what that might look like. And then we're just going to fill in these spaces here. Okay, so the billiard ball model was John Dalton, and it said that the atom was the smallest. You couldn't break an atom down any more than just the atom. So. So basically, you can't break an atom down into anything smaller, or another way of saying that is that there's no internal or external features. The big limitation of this was the fact that at the time Dalton developed his model, so at the time, atoms were known to combine to form compounds. Okay, and so then that suggests an internal structure. If they're combining to form compounds, then likely there's something else going on inside the atom that lets them do that. And since Dalton said there was nothing else inside that billiard ball, that was his major limitation, or the major limitation of his model. The Raisin-Bun model said that an atom is mostly, sorry, I'm going to say an atom is negative bits embedded in positive goo, or positive material. And so just remember, J.J. Thomson discovered the electron, which we'll talk about a little in a few minutes. We didn't really talk about any major limitation to the Raisin-Bun model, but I'm going to put in here it was contradicted by Rutherford. By Rutherford's gold foil experiment. Which then brings us to Rutherford with the planetary model. And so Rutherford discovered the nucleus. And he said that most of the mass and all the positive charge are concentrated in the nucleus. And the electrons orbit the nucleus. Electrons exist in an orbit around the nucleus. And his limitation was it contradicted Maxwell's theory of EMR. The Bohr model said that electrons exist in discrete energy levels that are a discrete distance from the nucleus. And his model also talked about emission and absorption spectra. His limitations, first of all, it's only for hydrogen. And it didn't describe why discrete energy levels. And the quantum mechanical model basically says that electrons orbit the nucleus as a wave. And the orbit size must equal a whole number of wavelengths. And there's probability involved in finding the electrons. Probability. And I'm going to put this under limitation, but it's not really a limitation of the model. It's just something that came out of the model was you can't know. What's wrong with this? Okay, so I'm just putting on there that the quantum mechanical probability model implies that it's impossible to know both the position and the velocity of the electron at the same time. You know one or you know the other, but not both. so then back to the atomic physics review booklet once you're finished with that. I'm just going to orient my board because it's not doing so well. Okay, so back to this. So I've got on there just C handout. So you remember that we filled that handout with stuff. Okay, and then we're gonna look at, like, kind of specifically at Thomson. So now the thing is I haven't built into this part review, kind of reviewing each of the individual experiments that relates to the model of the atom. So I'm talking about Thomson, but I'm talking about the calculations that are involved in that. But you need to know, it's implied in that you need to know sort of details of stuff, especially Rutherford's experiment and then J.J. Thomson's experiment. J.J. Thomson's experiment we're going to go through. But this, you really need to know here, these two actually, you need to know in detail. Make sure you have an awareness of that. I guess I'll talk a little bit about spectroscopy in the emission and absorption spectra in the notes, but I didn't really go over Rutherford's model. That's on here to kind of think about. So Thomson, he found the velocity of cathode rays. So he worked with cathode ray tubes, and he found the velocity of cathode rays by having balanced electric and magnetic fields. So Fm equals Fe, so QVB equals EQ, where your Q's cancel, and so then you end up with, in his case, he was solving for velocity, so it was electric field divided by magnetic field. And this is, like, the individual formulas are on your formula sheet, but this relationship here is not on your formula sheet. So whenever you get those kind of cathode ray questions or the mass spectrometer questions, you have to ask yourself is that if the ion or the particle is traveling through undeflected, then this is the analysis. If it's traveling through and it deflects in a circle, then you use the Fm equals Fc. So the charge to mass ratio of cathode rays, he found that by the fact that charged particles deflect in magnetic fields. They deflect in a circle in a magnetic field. So then what that leads to is Fc equals Fm. So mv squared over r equals qvb, or you can cancel out a velocity. So you have mv over r equals qb. And you can use that to solve for all kinds of things. Charge to mass ratio, you can solve for just the magnetic field, for the velocity, for the mass, for the radius, for momentum. It's just a matter of knowing that that's what happens whenever a charged particle moves in a circle. And Thomson isn't the only place where we find these two different ways of analyzing a situation. We also covered it in forces and fields. It came up there, like I said, with mass spectrometers. And this relationship, again, is not on the formula sheet. That has more to do with possibly if you get a question you don't really know where to start by drawing a free body diagram. Like draw the free body diagram of what forces are acting on the electron. Which I wanted to mention, you can write all over the diploma exam. Like you can write all over it, take as many marks as you want. They only ever look at the answer sheet. The other stuff is shredded. Okay, so looking at spectroscopy, and so related to this spectroscopy, this is also sort of the Bohr model of the atom. There's three different types of spectra that we talked about. Continuous, an emission or bright line, an absorption or dark line. So first of all, you need to be able to recognize from a picture whether it's continuous, whether it's an emission or bright line, or whether it's a dark line. So a continuous spectrum is all the colors with no gaps. It's Roy G. Biv with no black in it at all. The emission of the bright line spectrum is mostly dark with colored lines at specific wavelengths. It is the emission spectrum is what you observed at U of A when you did that, right? So if you can think about that, it was all black and it had just these bright bands, and it took a long time sometimes to find those bright bands, okay? Just by the nature of the equipment. And then an absorption spectrum is a continuous spectrum, so it's like Roy G. Biv, but then there's black lines in it where the colors are missing. So you need to know what each of them look like. You need to know how they're formed. So a continuous spectrum is a glowing solid. An emission spectrum is a heated gas. And if you can remember that you turned a light on a hydrogen tube. You sent electricity through a hydrogen tube, which heated that gas, which gave you an emission spectrum. And then an absorption spectrum is light shining through a cool gas. So you need to know what, how, and why for each one, basically. So what they each are, how they're made, and the why. And the why is only for emission and absorption. And so remember that an emission spectrum results from an electron moving down to a lower energy level. So if this is, that's the ground state. Okay, so we're going to call n equals 1. Maybe this is n equals 2, n equals 3, n equals 4. And if we've got an electron up here that travels back down this way, this is an emission spectrum. But in order for an electron to move down an energy level to give you an emission spectrum, it has to have been excited somehow to move up an energy level by absorbing energy. So what happens is it absorbs energy somehow. So an absorption spectrum results from an electron moving up to a higher energy level. So it absorbs energy in quantized amounts in the form of a photon or a passing electron. Once it's absorbed that energy, then that energy allows it to move up. So maybe you have an electron here that moves up here, and then that's an absorption spectrum. As soon as it gets up to that level, it doesn't like being there. It wants to go back to where it lives in its ground state. So it will immediately drop back down and emit energy. So a couple things on here that if it absorbs energy from a photon, it has to be the exact amount. I didn't write that down. Sorry, I have that written on the next page, so we just won't write that down. That's my fault. I rewrote my notes and then... So this just describes the energy transitions a little bit. So an electron at ground state can absorb energy and move to outer levels. And it can get its energy either from light, so from a photon. And if it gets it from light or a photon, then it has to be the exact amount of energy. The photon has to give up exactly the right amount of energy, then that photon doesn't exist anymore because it's absorbed, right? And that gives you the missing lines in the absorption spectrum. If it's from an incident electron, some sort of electron that's passing by that has kinetic energy, that electron can give the electron in the atom any amount of energy it wants. So it can give, the electron will just take what energy it needs, and then the traveling electron will continue traveling along, and it keeps whatever EK is left. And the thing to remember here is that electrons prefer being in their ground state. I'm going to put in their stationary states. So wherever they exist naturally, whatever energy level they exist in naturally, that's where they like to be. So they'll absorb energy to move up, but then they emit that energy right away and move back down again. And so then, coupled with this electron transition stuff, you can use energy equals h times f, or energy equals hc over lambda, to determine the wavelength or frequency of emitted or absorbed photons. So what you're doing up here is you're always finding the change in energy, which is the absolute value of the final energy minus the initial energy. And that is not on your formula sheet. These are on your formula sheet. Well, and I want you to kind of keep in mind here, too, that if you think about all the concepts we've covered, there's very few concepts where you're going to get more than one question on it, because there's so much. And I have a little bit of kind of comparison stuff I've been doing that kind of bothers me, and I don't really know who to tell it to, but I'll tell it to you guys. So the physics diploma is 36 multiple choice and 14 numerical response. You have from 9 to 11 an extra half hour. The math diploma exam is 36 questions total, and they have 3 hours to write. It's about 2/3 the size of the exam, and they get an extra half hour over the physics. So, to me, there's too many questions in physics. They're trying to test every single outcome, and they just can't. So that's got to change. So what I want you to do is, because I mentioned that on your diploma exam at the end, there's going to be 2 survey questions. Make sure you answer those honestly. If you feel that the diploma exam is just too big, write it. And you don't have to listen to me. You don't have to repeat my opinion. But I'm hoping that from that survey, they're actually going to make some choices. The one thing I really, really, really hope comes out of this is that the weighting of all diploma exams is taken down a lot. And that's supposed to happen. It's supposed to go down to be more like about 30%. Okay, they are sort of moving toward that. So then it becomes more like a normal. Yeah, exactly. Not now, but yeah. But no, the thing that's like. So a couple suggestions on that. Like, I mean, it depends what you're doing. Like, if you find that you're not happy with your mark on the diploma and has an impact on what you're actually able to do in the fall, wait till that announcement comes to rewrite the physics diploma. Or just, there's really only 3 schools in Canada that actually look at diploma exam marks. U of A, U of C, U of L. If you leave Alberta, nobody cares about your diploma exam marks. In fact, they prefer to not look at them, and they're advertising for that. Okay, so mass defects. Mass defect is the difference between the total mass of the nucleon, so the mass of the protons plus the mass of the neutrons, and the actual mass of the nucleus. So that's change in mass is equal to the mass of the protons plus the mass of the neutrons minus the mass of the nucleus. Okay, and that missing mass is equal to the energy used to keep the nucleons together. The other thing about the diploma is I think unless you're actually planning to go into a physics program, having taken physics and written the diploma is a big coup on your transcript. And unless like you really only have to be kind of worried about your low mark until you're trying to get into a physics program. But even that I don't think it's right. Yeah. Missing. Well, it does. Yeah, it matters for that kind of stuff. Like I mean, I shouldn't make light of it. Like it does matter kind of in terms of other things. It's always best to apply for as many as you can because a lot of scholarships go unapplied for and then unrewarded or unawarded, and they sit there and or not. You know, money just sits there and nobody gets it. Okay, so then switching gears a little bit and moving into isotope notation and nuclear decays. Remember isotope notation, AZX, where X is the element symbol. Z is the atomic number, which is the number of protons. A is the atomic mass number, or number of protons plus number of neutrons. Okay, and then we've got our radioactive decay. So the 4 types of decay, we did alpha decay, beta negative decay, beta positive decay, and gamma decay. And sort of the algorithm for doing that in there. So the alpha decay, the atomic number, the number of protons decreases by 2, and the atomic mass number, the number of protons and neutrons decreases by 2 because you're getting rid of a helium nucleus, which is 2 protons, 2 neutrons. Beta negative, you're expelling an electron. So your atomic mass number becomes 1 bigger because what you have happening is a neutron decays into a proton and electron, and then also an antineutrino. And then beta positive is similar, except you get a positron, and it's a proton that breaks down into a neutron and a positron, and it expels the positron and a neutrino. So this is with quarks. And then gamma is just a gamma photon, and it has no impact. If it occurs on its own, it has no impact on the atomic mass or the atomic mass numbers. But usually that gamma happens with one of those three types of decay. Decay chain, so just when you've got like more than one decay happening, there's a chart. We did one of those in our notes. And determining the type of radiation by deflection in a magnetic field, as well as by deflection in a magnetic field, or by shielding, how it can be shielded. Okay, half-life. The half-life formula, which is, this is what's on your formula sheet. That way, this is not on your formula sheet, so you need to know that that N is the time divided by the half-life. And you remember, you're not expected to know logs, but by all means, if you like using logs, use them. And then decay graphs, right, where this would be time, this might be percent, and it looks like that, it's exponential. And remember, if no mass is given, then you're usually, NO is 100, right? For 100%, you're determining what percent is left at the end. Remember, fission and fusion both release massive amounts of energy. Fission is splitting the atom. It's how we get nuclear power. And the products are radioactive. Fusion is combining, fusing, or combining atoms. It happens in the sun and stars. Products are benign, so are not harmful. And I think it was actually on your test where you had like a numerical response question with 8 different things, and you had to pick out all the stuff that went with fusion. That's a really, really common fission versus fusion question to get. It was like a numerical response, and it listed like 8 different things, and it would say things like, is, you know, splitting the atom or fusing the atom, products are harmful, products are harmless, occurs in the sun, occurs in power plants. You had to pick out the ones that went with fusion. Oh. Okay. Mass energy equivalents, or nuclear energy released, or binding energy. For all of them, we use the same formula, the delta E equals delta MC squared. This is on your formula sheet. Usually for delta M, it's either mass defect, which was on the previous page, or change in M is equal to the mass of the reactants minus the mass of the products. Okay? And then that missing mass from what you started with and what you end up with converts to mass, which then converts itself to a large amount of energy. And don't forget to square it on that, because that students are always forgetting to square that, forgetting to square speed for kinetic energy. So electron, positron, antimatter, matter-antimatter annihilations. So just a positron plus an electron will collide and form 2 gamma rays. So understand that. And that we've got here charge, momentum, and energy are conserved. The fundamental forces in mediating particles, and so in order of strength, strong nuclear, the electromagnetic, weak nuclear, and gravity. Gravitational, just to keep the grammar right. Gravitational. Okay, and then the mediating particles for the strong nuclear is a gluon. For the electromagnetic is a photon. For the weak nuclear, it's the weak gauge bosons. Think on your chart, it's W plus minus and Z naught. And gravitational is a graviton. But I'm putting this, which to me sounds like a video game. I'm going to put this in brackets because this is the one that hasn't been observed. And so then this goes from strongest to weakest. And then just a few things at the end here. So know what antimatter is, what a cloud chamber and a bubble chamber are, and how to analyze the tracks, which we did sort of in the first few days of this year. Particle accelerators, and then the subatomic particles. I've got that on there, but all that you really need to know from that is what we already did here, which was the quark stuff. The quarks. So I'm going to add that over here. So you just need to know that the main thing about the particle zoo is that a proton is up, up, down in quarks, and a neutron is up, down, down. Remember, dud for neutron. Okay, and that's atomic physics, and that's the review of the course.